Doing well. My name is Shriya Bansal and I'm currently working as a software engineer at Microsoft. And in this video, we are going to start with the second aspect of memory allocation, which is non-contiguous memory allocation. So in non-contiguous memory allocation, right, what we do is it is allowed to store the processes in non-continuous manner. Like some process can be there, some process can be somewhere else. Now, there are different processes or different techniques to actually make sure that the non-contiguous way of memory allocation can be implemented. We have paging, segmentation, virtual memory paging as well, also known as demand paging. So we'll take a look at all of them one by one. In this video, we are just going to talk about paging. So main memory is basically divided into equal size blocks and it is known as frames. So you have your main memory, you will divide it into equal size blocks and it will known as frames. Okay, those blocks are known as framed. And each process is also divided into equal size block. So here the division is happening at both the memory level as well as the block level, as the process level. So you will divide the process memory also, call it frames, each and every partition. You divide the process also and call it pages. Now a process is loaded by loading all of its pages into the available frame. So what you do is you had entire memory, you basically divided it. You had the process, you divided it, and each and every divided part of a process known as pages are loaded into frames. Okay. And it may not be done in the contiguous manner. For example, this is your physical memory, right, where you are actually storing, right, all the processes, and here you have the CPU basically have the process. Okay. Now here what will happen over here is this is a very high level overview of how we are going to work with. So just to tell you, here what will happen is the paging technique basically divides the physical memory or the main memory into frames. Okay, and here we also divide the logical memory, okay, or you can know the memory that is taken by a program or a process into pages. Okay, and this is basically happening for the secondary memory, or you can consider as a process as well. Okay, so this is division happening, right? Everything is divided, and each process is basically divided into parts, right, where the size of, so here we have a process which is divided into parts and the size of every process is equal to the size of the page over here. Okay, so what happens in this is, we'll come to this diagram again. Here you can see one thing very clearly happening over here is that we are converting the logical address into physical address. Okay, so this is a very important point over here, that whenever we are converting, right, whenever we are doing the concept of paging, we have to understand like some important things, that the CPU always generates the logical address, which we have discussed, and the physical address is basically a mapping to the logical address. Okay, so in order to access them, so CPU generates logical address, but in the main memory you consider physical address. Okay, so you have to basically convert the logical address to physical address, and a logical address always have two things inside it. Okay, a page number and the page offset. Okay, this is basically written over here as well, that a logical address or a virtual address is generated by the CPU. Okay, and the logical address space or the virtual address space, which we have already talked about, is the set of all the logical addresses generated by a program. And the physical address is basically the address which is actually available in the memory. And physical address space is nothing but a memory mapping to the logical addresses. So here, whenever an address is generated by the CPU, which is the logical address, it is always divided into two parts: page size, page offset. Page number, okay, sorry, over here is used to specify which page of the process from the CPU, right, from which the CPU wants to read the data. So every process is divided into pages. So CPU will read a particular page of the process. So page number tells you that if there is a process which has 10 pages, numbering are 1 to 10, the CPU basically wants to reach, let's say, page number 3. Okay. And page offset means that the it basically used to satisfy the specific word on the page. So on a page also you have a lot of information available, right? So page offset means that on the particular page number that you are, which bit, right, or which word are you trying to read? Meaning number of bits that are required to represent a particular word in a page, or the page size of the logical address space. Okay, so that is what a logical address will already be contained. So there is a CPU, it will generate a logical address which will have two part. Okay, it will have the page number, and it will D basically stands for the page offset. Okay, now first we're just understanding the components of this diagram, then the entire paging concept will be stitched together. Next, we have the concept of page table over here. Okay, we'll try to understand what exactly the page table is. Just a second. Okay, let's talk about it here only in this. So page table basically contains the base address of each page in the physical memory, because if you will see over here in this, right, we have physical address. Even for physical address now, it is divided into two parts. It's never just a single address. Page, it basically has like I would say a frame number, and it also has a frame offset. Okay, so here the frame number is basically, I would say, used to indicate the specific frame, okay, where the required page is stored. So I told you, right, every page of a process is mapped to a frame. So frame number basically tells us that which particular frame that particular page is stored in. Okay, and frame offset basically is used to like represent a particular word, okay, that has to be read from the page over here. Okay, so that is what we basically say, that frame offset is the number of bits that are required to represent a particular word in a frame, right, or in the frame size of the physical address space. Okay, so that is how the overall idea works. And what does page table does over here is that page table basically contains that mapping, okay, that which page number is basically stored in which frame. So to know that mapping, we basically use the page table. Okay, it basically provides the corresponding frame number where that page is stored in memory. It's more or less like a hash map. Okay, this page number is stored in which frame, which will be basically derived from the page table. So I'll write this down as well. Okay, page table basically provides the corresponding frame number where that page is stored in the memory. So it's like something like this, like the page number 2 is basically stored in frame number 5. Okay, so it's something like this kind of a mapping which is basically present in the page table, because you want to know, because you're not storing all the pages of a process at one location, right? So if you're storing it at multiple locations, you should know where all those locations are. So the page table basically maintains that information for you. Okay, so this diagram now should help you give the bigger picture over here about what is happening. Okay, here basically we are like it is basically helping us to understand the translation of logical address into the physical address. Okay, here what you will see what is happening over here is we have a CPU which generates the logical address, right? Here we've using that, right, we have the logical address which is of two types. Okay, here the page number the frame offset, and then we just basically do the mapping and store the particular page of a process in memory. Okay. So remember that the hardware implementation of page table can be done by registers, right? How you are storing this kind of a mapping, but the usage of registers for the page table is satisfactory only if your page table is small, because you have to store the page table also in memory, right? So if your page table is small, you can use registers for that. But if the page table has a lot of entries, right, then it is not possible to store all of it inside the, I would say, inside the registers. Okay, for that, now if your page table is very big, you have to use translation look aside buffer, which is a small special fast lookup hardware cache. Okay, because we want to make sure page table are very important over here, right? Because they are the ones which is actually storing all the mapping. So the way we access the page table, right, should be really, really fast over here. And for that, what do we do is, instead of using registers, there is a small and a quick solution that we use, which is translation look aside buffers. Okay, translation look aside buffer is basically a associative and a high speed memory. So now that we have talked so much about, what exactly paging as a technique is, it's also important to talk about some of the advantages and disadvantages of paging. So in terms of advantages, what we can say is that paging as a technique reduces external fragmentation, which was the very big problem when we were dealing with continuous memory allocation. So in non-continuous memory allocation, paging as a technique, I would say, saves that problem a lot. Okay, it reduces external fragmentation, but it still cannot work for internal fragmentation, right? Inside a partition, if something is pasted, it will still be there. Apart from that, paging is simple to implement and it is assumed, okay, as an efficient memory management technique. Okay, paging as a technique is very simple to implement. Paging, you don't require a lot of, I would say, hardware implementation and a lot of explain or complex concept. It's very simple to implement and it's a very effective and efficient technique also, due to the equal size of the pages and the frames. Okay, swapping becomes very easy. Always remember that the size of the page is always equal to the size of the frame, so that it can exactly, fit inside of a particular process. Apart from that, page table requires extra memory space. Okay, so it may not be a very good choice where, you have a very small RAM. If you have a very small RAM, what will you do is you'll actually occupy a lot of good space just to make, just to occupy the page table. So in that scenarios, paging, it might not be the very best technique. Okay, so I hope the concept is paging to clear everyone, right? I hope I was able to help you understand this topic. And now we are going to move to the next video and talk about segmentation. All right, thank you.